Space is big, you just won't believe how vastly, hugely, mind-bogglingly big it is. You may think it's a long way down the road to the chemists, but that's just peanuts to Space Douglas Adams. It's funny until it's not, because once you let that line really sink and something strange happens, you stop laughing, you feel it tug at the edges of your reality like your mind just bumped into a wall it didn't know was there tonight. We're going to push straight through that wall. Welcome to Late Science. This is not just a video, it's a journey, a slow expanding meditation on one simple, impossible question. How big is the universe? Not in numbers, not in statistics, but in something you can actually feel. Because if the universe really is as big as we say it is, if it's growing faster than the speed of light, if it holds trillions of galaxies, each with hundreds of billions of stars, if it's been around for nearly 14 billion years, then what does that make you? What does that make your life, your problems, your plans, your breath? Over the next few minutes, we're going to zoom out farther than your brain wants to go, farther than it can go, at least without breaking a little. We'll begin with the ancient stargazers, move through early telescopes, modern science, and the invisible edges of the observable cosmos. But we'll also dive into the emotional fallout of confronting scale, because numbers are cold, perspective is personal. If you feel your sense of self start to dissolve, if something inside you stirs with awe or fear or wonder, then like this video, comment with the moment that hit you hardest, and subscribe to Late Science, because this is only the beginning. Now take a second look around the room you're in, the walls, the furniture, the objects you own, the planet spinning beneath you. All of that exists inside a galaxy, spinning inside a filament stretched across a universe that's expanding so fast light itself can't keep up. And we're going to trace it all one part at a time. In the beginning there was light, but before that there was silence. Let's begin. There's something visceral about standing under a truly dark sky without streetlights or building glow. The Milky Way spills overhead like a river of diamonds, each star twinkling with age and distance. In that moment, you might feel your pulse slow, your usual concerns dissolve, and a quiet clarity take their place. Psychologists call it awe, an intense emotional state where your sense of self shrinks and your sense of connectedness expands. It's more than poetic, it's physiological. Blood pressure lowers, heart calms, and stress retreats into the shadows. That feeling is no coincidence. Researchers have found that this emotion triggers the release of calming hormones, quiets internal chatter, and even lowers markers of inflammation. In studies, people who regularly seek out awe through stargazing or natural beauty report less anxiety, more happiness, and a deeper sense of meaning. And it isn't limited to remote wilderness. Just a few minutes gazing at rooftops and city stars can still spark the same mental shift. This emotional release is essential when we approach cosmic scale, when we begin to discuss light years and galaxies. Our brains need to unclench. If your mind is stuck in daily stress, the numbers bounce off your awareness like static. But in this calm openness, each figure becomes a revelation. You start to breathe with the universe. That's why part 2 isn't about measurements or history. It's a ritual. It's preparing your heart and mind to receive the grandeur at the core of this journey. As you sink into that awe, your world shrinks, your clothes, your commute, your arguments into a silent backdrop. And the cosmos opens. This resets anything that stood between you and wonder. Now, you're not just watching a video, you're stepping onto a shared platform of astonishment. From here, every cosmic revelation will resonate deeper. You'll not only understand the scale, you'll feel it. In the early 1800s, the cosmos still whispered its secrets without revealing its scale. Telescopes had sharpened our view, but the true distances to stars remained elusive. How could anyone grasp light years using nothing more than geometry and patience? Enter Friedrich Bessel, a methodical German astronomer around 1837 to 38. He turned a powerful new instrument, the Fraunhofer, toward a faint, fast-moving star called 61 Cygni. With this precise device, he measured tiny shifts in the star's position caused by Earth's orbit, an effect known as parallax. Imagine measuring an object so distant that its shift mirrors the movement of a tiny coin seen from miles away. Bessel logged over 100 careful observations across seasons. By comparing the star's position against distant background stars, he detected a minute wobble, just a few hundredths of an arcsec. From that, he calculated a distance of about 10.4 light years, an astonishing first. The universe now had measured soon after other astronomers confirmed stellar distances. Thomas Henderson measured Alpha Centauri from South Africa, and Wilhelm Struve charted Vega, but it was Bessel's parallax of 61 Cygni that set the cosmic scale firmly into human hands. This wasn't just data, it was a portal. Triangles and patience transformed the night sky into a quantifiable domain. Suddenly, distances once imagined became numbers still vast, but within the grasp of human minds. That foundational feat, measuring one star, paved the way for astronomers to build longer ladders from nearby stars. They would ascend through techniques like Cepheid variables, supernova, and redshift, each rung pushing us farther into the deep cosmos. But for now, this is where it began, with Bessel's quiet persistence under Königsberg skies, defying human intuition. He taught the world that cosmic distances could be known, bridging empty space with geometry, and resolve. Building on Bessel's breakthrough, astronomers realized they needed a brighter, more distant ruler to reach galaxies beyond our Milky Way. That ruler came in the form of Cepheid variable stars, pulsating beacons whose brightness flips on a reliable rhythm. These stars, discovered in the late 19th century, pulsate with a period directly tied to their intrinsic brightness. Measure how fast they brighten and dim, and you can deduce their true luminosity. Then compare that with how bright they appear, and voila, you get their distance. In the 1920s, Edwin Hubble used this technique to resolve a cosmic mystery, the nature of nebula like Andromeda. By spotting Cepheids in Andromeda and calculating their distance, he showed that these nebula were not part of our galaxy. They were entire galaxies themselves, each containing billions of stars. That meant the universe was exponentially larger than anyone had imagined. This was a revolution. We went from knowing distances to a handful of nearby stars to gauging entire galaxies millions of light years away. Cepheid variables, with their rhythmic pulse and predictable luminosity, became the second rung on the cosmic distance ladder, lifted by Bessel's first geometric step. As we peer deeper, we realize the universe isn't just vast, it's populated with countless cities of stars. Each Cepheid lights the path, anchoring distant galaxies to our expanding cosmic map. After Cepheid variables lit the path to nearby galaxies, astronomers faced a new challenge, measuring distances to galaxies so far away that no individual stars could be resolved. For that, they needed something brighter, something explosive. That something was the Type 1, a supernova. These aren't ordinary stars, they're detonations, white dwarf stars in binary systems that steal matter from their companions until they reach a critical tipping point. When that limit is exceeded, the star collapses inward and then detonates with unimaginable force. The explosion is so bright, can be seen across billions of light years, often outshining an entire galaxy for weeks. But the most useful part, these explosions are reliably similar in brightness nature. It seems to give us a cosmic flashlight, because Type 1, a supernova, explode under nearly identical conditions. They reach a nearly uniform peak brightness. This makes them perfect standard candles. Once astronomers know how bright the explosion should be, they compare it to how bright it appears from Earth. The difference tells them how far away the explosion happened. The brilliance of this method is that it extends our reach. We're no longer limited to our galactic neighborhood. With these supernovae, we can measure distances to galaxies billions of light years away, galaxies too distant and dim for even our best telescopes to resolve in detail. But there's more. These supernovae don't just give us distances, they tell us something deeper about motion. When astronomers charted the distance to many of these galaxies, they realized something shocking. The farther away a galaxy is, the faster it appears to be moving away from us. This relationship, distance and velocity, is the fingerprint of an expanding universe. It's what led to the formulation of Hubble's law. The universe isn't just vast, it's growing vaster with time. That realization shook the foundations of physics. The cosmos is not static, it's dynamic, stretching, growing, evolving. Every supernova flash, every measured distance, is a note in the grand song of expansion. This part of our journey changes the tone. We are no longer bound to a finite sky. The universe is not just big, it's becoming bigger. The stars are not fixed in a dome, they are hurtling away from one another in a silent, accelerating ballet. For decades, astronomers believed the universe expanded in the aftermath of the Big Bang. But the force of gravity would eventually slow that growth, maybe even cause it to reverse. That made sense. Every explosion eventually settles, every stretch pulled by weight should strain and sag. But something wasn't adding up when scientists used Type 1, a supernova, to measure the distances and velocities of extremely remote galaxies. They noticed a terrifying detail. The farthest galaxies weren't just moving away, they were accelerating. The deeper you looked into space, the faster galaxies seemed to retreat, not in a straight line, not in a steady drift, but in a runaway expansion, as if space itself were being pulled apart by some invisible force. This revelation struck like lightning. The universe wasn't slowing down, it was speeding up. What could possibly be pushing galaxies apart faster and faster? It wasn't gravity, it wasn't matter, it was something else, something that didn't cluster, didn't shine, didn't slow. It became known as dark energy, not because it's related to darkness, but because we have no idea what it really is. Imagine blowing up a balloon expecting the stretch to ease, only to find it stretching faster with each breath. That's what dark energy is doing to space, not only between galaxies, but between superclusters, between vast voids. It's not just carrying galaxies away, it's creating more space between them, making the distances unbridgeable. And here's the strangest part: dark energy doesn't seem to weaken, it doesn't dilute. As the universe grows, it persists. In fact, it dominates. Today, astronomers estimate that nearly 70% of the entire energy in the universe is this invisible accelerant. The stars, planets, dust, everything we can touch or see makes up less than 5%. Let that sink in. Almost all of reality, by volume and by force, is made of something we cannot touch, see, or fully explain. And yet it defines our fate. This is the moment in our journey where all turns to something deeper, unsettling curiosity. If everything is moving away from everything else faster and faster, what happens in the end? Will galaxies one day slip beyond our view? Will stars wink out forever? Will the sky grow dark, not from lack of stars, but from unbridgeable space? We're not just measuring distance anymore, we're measuring destiny. Once we realized the universe was expanding and accelerating, the next question was chillingly simple: how does this end? To even guess, we first have to understand how space itself might be shaped. It's easy to imagine the universe as a giant balloon or an endless plane, but space is more complex than any surface we can draw. Its shape isn't just geometry, it's destiny. Physicists broke it down into 3 possible forms: flat, open, or closed. If the universe is flat, like an endless sheet, expansion can continue forever, slowing but never stopping. If it's open, like a saddle curving outward, it will also expand eternally, only faster. But if it's closed, like a sphere, expansion might one day halt and reverse, pulling everything back together in a fiery collapse. The big crunch. For years, no one knew which shape we lived in, but thanks to precision measurements of ancient light,